Swayam Prabha. Digital India. Educated India.
In this lecture, we will mainly discuss about the construction of hydrophobicity profiles and the applications. Earlier, we discussed on different types of applications of these amino acid sequences. So, what are the various parameters or features or properties we discussed in the previous class?
So, amino acid composition,
amino acid occurrence, amino acid composition, molecular weight, pair preference and so on. So, what is amino acid occurrence?
so number of
It is
times.
essentially number of times each amino acid occurs in a protein sequence. Then composition normalized with the chain length. So, the difference between amino acid occurrence and composition is normalization with the number of residues in a sequence. Then we discussed about molecular weight. So, we can calculate the molecular weight by substituting appropriate weight for each amino acid residues and subtracted with the water molecule, right, 80 into n minus 1 water molecules, because when you form the peptide bond, it is elimination of one water molecule. Then we discussed about the pair preference, right, how far residues occur next to each other, A with A with D and so on. Then we discussed about couple of applications. One major application we discussed is how to distinguish between different types of proteins. Because proteins have different functions, they have different structures. So, whether it is possible to distinguish between these two types of proteins based on the amino acid sequence information. So, we discussed based on the parameter or based on the property amino acid composition. We used amino acid composition for the two sets of proteins, and for the unknown ones we compared with the known ones and then we decide depending upon the deviation. We can also do with the correlation, right. Also we can use different properties. So, also we discussed about the amino acid properties, right, for a average property for any given sequence, right. Each amino acid have the unique values. So, we add up together normalized with the chain length, that will give the average amino acid property values. So, now what is hydrophobicity profile, right, because name itself tells it is the plot of the hydrophobicity indices versus amino acid sequence. For example, if you take any protein sequence, so you can make a 2D plot. So, x axis we give about the amino acid sequence, y axis you write the hydrophobicity. Each amino acid has a value depending upon the hydrophobic character of the residues. So, depending upon the amino acid sequence, the residues in the sequence, so we can make a plot for each values. When you connect, then we will get a plot. So, we will see how to construct a plot with an example. We have the sequence, right. For example, this is the amino acid sequence in which format? Faster format, because you can see the started with the greater than symbol. Okay, here you have the amino acid sequence. So, I made some numbers for the 20 amino acid residues based upon their hydrophobic behavior. For example, if you take the highly hydrophobic residues like isoleucine, valine, leucine, phenylalanine, I put value of 2, and less hydrophobic I put value of 1, and the polar residues I give minus 1, and the charged residues I give value of minus 2. So, now we take the amino acid residues versus these hydrophobic indices. So, what is hydrophobicity profile? It is a plot connecting a sequence versus the values, right. So, here what is the sequence? M, E, N, L, N, M, D and so on, right. So, here we can put the hydrophobicity value. So, first one is M. What is the value for M? 1. So, you can put here this is 0. So, here you can put 1, 2, minus 1, minus 2. So, M equal to 1. So, you plot here Then the second one E, what E is, what is the value of E? Minus 2 here, and the N minus 1, L plus 2, this N minus 1, M plus 1, D minus 2, and so on. Then we connect, right, we connected. So, when you construct a plot, we can see some sort of patterns. These hydrophobicity profiles will provide you a specific patterns which will be helpful to identify some secondary structures, or you can see any specific motifs, or you can see any segments, right, which are traversing the membrane and so on. So, there are various software available to make a plot, right. So, one of these is available in the literature, that is called a 3D Insight. This will consider various properties. It will take the hydrophobicity values along with other properties to make a graph, right. X axis is the amino acid index and y axis is the hydrophobicity profile or any different properties. In this slide, when I made this profile, I used a value of 1, 2, minus 2 and minus 1. Actually, all the 20 amino acid residues contain specific values, right. So, I give couple of examples. One is the Nozaigi-Tanford-Jones scale. This is the first scale derived for the 20 different amino acids using experimentally. Directly we cannot calculate the hydrophobicity values. So, they did in direct way, that is relative solubility of each amino acid residues in water as well as in ethanol. So, they did the relative solubility, right, and converted the solubilities into hydrophobicity. So, if you look into these 20 different amino acid residues, right, we can see a specific residues which are high values and some of them they have less values. So, if you see this one, can you name few residues which are highly hydrophobic? Tryptophan, right, isoleucine, right, phenylalanine, right. So, these leucine, so these residues are hydrophobic because it contain aliphatic groups or aromatic groups. So, they are hydrophobic. So, in the partition coefficient, even the relative solubility, they also showed that these residues are highly hydrophobic. On the other hand, if you look into the charged residues or polar residues, for example, if you have serine or you have aspartic acid, right, or you have the glutamic acid, you can see that the values are less compared to the hydrophobic residues. So, if you make an average value, so you can easily discriminate the hydrophobic and hydrophilic residues with these numbers, right. This is one example which we obtained experimentally. Likewise, there are several scales available, right. I show another example. This we obtained from computational analysis. What we did here, they constructed a different data set of proteins and they assigned the values for each residue which are influenced with the neighboring residues. For each residue, they identified the residues which are occurring within the limit of any specific radius and then see what are the residues which are within this limit. Then they assign the experimental value and then finally they derive these final scales. Right. I will explain about this development of this scale in later classes. Fine. So, if you see in this scale, here also you can see the real situation, right, as we discussed earlier. So, they have some of the hydrophobic residues see like cysteine, tryptophan, isoleucine, they are highly hydrophobic, and several the polar residues and the charged residues like the lysine, and you can see the case of aspartic acid or glutamic acid, and these residues they are polar in nature. And major difference we find from these two scales, that is mainly in proline. Proline they did the relative solubility, proline has a ring. So, you can see this is hydrophobic in this case, but if you look into the location of this proline, it is mainly surrounded with polar residues. This is the reason why the proline is polar in this scale, right. Many scales they assign proline as a polar residue. So, we can see some differences and similarities, and most of the scales currently we have more than 100 indices are available. So, they have qualitatively they have similar behavior. So, now I show one example where we can construct the plot. So, here it lists up several properties, and here we have several hydrophobicity values. For example, the hydrophobicity values given with Eisenberg, also the Cayley-Liddell scale they developed in 1982. Then this is the hydrophobicity scale. So, we have different scales. If you want to make a plot, right, we first take the PDB code or amino acid sequence, right. This is the PDB code and here we take the L chain. So, if we selected this hydrophobicity scale, and if you click, right, then you will get the plot. What is x axis?
Change.
Amino acid sequence, right. What is y axis? Hydrophobicity value, right. So, you can see the plot connecting the sequence and the plot. Some cases you can infer the information, some cases it is not. If you see the here, it is kind of clusters. So, you can see the zigzag positions up and down on this case. So, if you cannot infer anything from the single residue plot, right, most of the cases you can find some patterns, then you can also try to get some window average. In this case, it is possible to get the average. So, for example, if you click on the plot with smoothing with box, in this case you can smooth for any window length. For example, if you have an amino acid sequence like this, so if you take the single residue plot, they plot for each residues, they have the hydrophobicity values, they plot. If you have a window length, for example, any residue, if you take a window length of 5 residues, right, for example, window length 5. So, what they do? So, they make a window considering 5 residues, 2 from left side, 2 from right side, right, for the N and C sides. So, this is central one. So, they make a window of 5. So, what they do? They calculate the average value and plot for the central one. Right, for the first residue, we do not have the left side residues, right, first 2, if we have the window length of 5, and all other residues, they have 5 residues length. So, now if you do this, for example, if you take the smoothing box of 9, then we will get the plot like this. Now, can you see the difference between the previous plot and this plot? Yes, here you can easily identify some regions which are highly hydrophobic in nature and some regions which are less hydrophobic in nature. For example, if you see here, all the residues are highly hydrophobic, and you can see somewhere here, right, some place here, and some place here, right. Here you can see this completely polar charge residues or polar residues. So, when you have this one, this will tell you that there is a stretch of residues which are highly hydrophobic in nature with 1 or 2 polar residues in between. Because of that 1 or 2 residues, in the first plot you can see a zigzag, because that polar residues as less hydrophobic is down. Here, because the average, this compensates maybe somewhere here, right, the residues are high hydrophobic. And interestingly, if you see this protein, this is a membrane protein, right, as I discussed earlier, the proteins which are embedded in membranes, right. So, these residues, they span in the membrane, if there is a membrane. So, here this is the protein, right. So, the region is the membrane. So, this response resembles this one. So, equally, if you can make a plot, this plot has some applications to identify the regions which are inserted into membrane, right. So, if you can use these hydrophobicity profiles, right, to get several other information. So, this is another behavior which are related with hydrophobicity, that is called amphipathic character. What is the meaning of amphipathic?
Both charge.
Both, right, 2, amphi means 2, right. So, either this is high or low. So, this will give you the information regarding the periodicities of the polar and non-polar characteristics of sequence. How to get that? You have the numerical hydrophobicity values, you assign the values and then see are there any periodicity in one dimensional plot. How to do this? For example, if you take alpha helical segment, right, how many residues per turn? 3.6 residues per turn. So, for if you have a helix, right, we start from here, right. So, one turn is up to here, right, this way and this way, right. So, if you have the helical axis, you can put the residues, okay, 1, 2, 3, 4, the same way 1, 2, 3, 4. So, you can make it. So, in this case you can see there are 2 residues on one side and 2 residues on the other side. So, they show a periodicity of these residues, right, at different positions. If this I, for this I plus 1, I plus 2, I plus 3, I plus 4. So, you can see the periodicity, right, I plus 5. So, between this I and I plus 4. So, this 1, 2, 3, 4 and this 5, right, 1 and 5 they will be in the same phase, and likewise you can see the 2 and 6. So, if you have a helical segment, you can make on 4 adjacent edges, right, you can put 1, 2, 3, 4 in the direction of the helical axis. Then you can calculate the average hydrophobicity of each edge. For example, if you take this plus same is here, same is here. So, you can see I plus j with the interval of 4 and see how many residues in that particular place. For example, if you see this periodicity, this is I, this I plus 1, I plus 2, I plus 3, I plus 4 and I plus 5. You can see the periodicity, 2 residues are less hydrophobic here and 2 residues are at high hydrophobicity, then again 2 less and 2 high. So, if you have this type of patterns, then we can say these residues are part of alpha helix, these residues constitute alpha helix, right. So, if we have a sequence and if we make a plot with the hydrophobicity and if we see any of these patterns, then we can say that okay, these residues can form alpha helix. Then the second is how to calculate the power of ambipathicity. For example, if you have 2 helices, they are ambipathic and which one is more ambipathic than the other. For in this case, right, you can calculate the power of ambipathicity A alpha. So, if 1 and 2 are high and 3 and 4 are less, then take the first 2 and the second, third and fourth and get the absolute difference. In this case, okay, here take these numbers as 1 and these numbers as 2, right. Okay, this is I plus 6 and this is I plus 7. So, then take the difference, this will give you the power of ambipathicity. Okay, you can see the A alpha either A plus 1 minus A 3 plus A 4 or if A 1 and A 4 minus A 2 plus A 3. This is in this case, right. For example, if it is like this, right. So, this is 1, 2, 3, 4, right, A 1, A 2, A 3, A 4. If this is the case, this will come together, right, A 2 plus A 3 and this will come together, right, you can see a difference. So, from this one you can see whether they are amphipathic or not, but if you look into the literature, about 70 to 75% of the helical segments of known structures, they are amphipathic in nature. In this case, if you use this type of profiles, you are able to predict to some level of accuracy, at least to 65 to 70% of accuracy, right, in any sequence. This for alpha helix. How about in the case of beta sheets? Yeah, in the case of beta strands, right. So, you can see there is 2 phases, right, you have 2 phases, one is here, one is here, right, alternate phases. So, one is having high, another case is low hydrophobicity. So, in this case you can calculate beta I, this is summation h I plus j by n, where here these intervals of 2. In the helix we have interval of 4, in the beta sheet interval of 2, right, with up to m, where m is the number of residues in each strand. So, calculate the beta I, this is equal to sigma h I plus j divided by n, right, for n is the number of residues in each phase either here or here. So, now we have the patterns. Okay, you can see the x axis the amino acid sequence, y axis the hydrophobicity index. So, here these are the hydrophobic values of different amino acids. So, this is the average value. So, this A1, A2, right, A3, A4, right, A5, A6. Okay. So, if you see that the power of the ambipathicity you can calculate, maybe this is one side, this is the another side, this is one phase, second phase, then add up all these together, take the average and add here everything together and take the average. Finally, you can get the values, right, you can get beta 1 minus beta 2. So, you get the amphipathic behavior of this particular beta sheet. So, in the structural analysis also showed that about 65% of the beta sheets they possess amphipathic in nature, right. If you take all the beta sheets in the known structures and we construct the plots and you can see about 65%, right, they are in amphipathic in nature. So, now what are the other applications of this hydrophobicity profiles, right. Here we discussed 2 cases, right. One is the alpha helices. What is the periodicity in alpha helix?
1 plus 4.
Yeah, 2 on one side and 2 other side. What is the periodicity in beta sheets? 1 1, right. We have the alternate high and low hydrophobicity patterns. So, some cases, for example, if you get the hydrophobic behavior, right, this is the average value. For example, this is the average value if you take, and all the residues are highly hydrophobic. For example, put this sequence, A is hydrophobic, I is hydrophobic, L is hydrophobic. So, all residues are hydrophobic. So, we have the pattern of highly hydrophobic residues. If this is the case, this will resemble a type of protein a type of segment. Which type of segment? This membrane spanning alpha helices, right. So, this is the membrane spanning alpha helices. So, if you make a plot, you can get some information, right, from primary sequence, right. So, without having any information, if this character provides a specific information, at least we can develop from that point of view. So, constructing heterogeneous profiles will give some information from the sequence. This is another pattern just I discussed earlier. This is the beta sheets, right, amphipathic character. So, because you can see the red one is the hydrophobic and the black one is the hydrophilic. So, you can see alternating hydrophobicity. So, this will give the pattern for the beta strands. So, now in the amino acid sequence, it is also possible to identify any specific motifs or patterns. In this case, we define a specific definition for defining patterns. For example, we take any sequence, for example 5 residue segments or 10 residue segments, whether they possess any specific patterns. So, in some cases we discussed earlier about conservation. So, what is conservation?
Residue is conserved.
Yeah, in any position a particular residue occupies the same position in all the homologous sequences. In this case, the residue is said to be conserved, right. If a residue is said to be conserved, then we have to keep that particular residue in all the positions. For example, if you have specific motif G, X, X, G motif or any specific motif called D, R, Y motif, right. This is for something for the GPCR, this is for the disulfide bridge forming enzymes. So, if they have some specific motifs, then we can search any specific motifs in the whole database and see whether there is any characteristic pattern for that particular set of proteins. So, in this case we define patterns, right, using some sort of notations. So, here we show on sequence, we use some residue names. For example, here this means the residue glycine is conserved at particular position, right, that maintains the same residue at the particular position. So, we cannot change this for this place as well as at this place. They put X, what is the meaning of X? Any residues, right, we can all the 20 amino acid residues, right, any residue, right, is allowed at this particular position. Then we have these numbers, number means number of times, with 2 means 2 times we can have follow the same notation. Then we use the square bracket. For example, here we put LIVM. This will give you the choice of amino acids, any of these 4 residues. Among these 4, either L or I or V or M, any residue can accommodate at position number 1. Then we have these curly brackets. If this is brackets, this is excluded, right, this is not allowed. For example, if you put CF, C and F should not be in that particular position, right, that is they give the exception that these are not allowed. Then you put X for any amino acid, N means number of times. If you I show this one, how many amino acids in this pattern? This is 1, 2, here 2, right, 2 plus 2 4, 5, 6, 7, 8, 10, 14, 16, 17, right, 17 amino acids in this pattern. So, how to write a pattern in this case, right, if you take this one. So, position number 1, which residue can come to position number 1? Anything, residue, for example, I put B. For the second position, again we put B, right, and third and fourth, anything, right, you can put it 2 times B again, right, and this position G, because here we cannot do anything, so we have to use G because G is conserved, and in this here N, Q, okay, we can put Q. So, this is X, right, X you can put P, right. So, here A, okay, then two any residues I, IA, right, and here L, M, F, V. So, because L is allowed, M is allowed and F is allowed and V is allowed 4 times, because of 4 times you put 4, then 2x, right, AA and finally G. So, you can write a pattern and then you can use this pattern to see whether you can see this type of patterns in all the sequences of particular type, right. I will explain one with one example. So, now this you can write a code to get the pattern, or also this tool is available in the PIR. What is PIR? Protein information resource. Actually, they first initially developed for the protein sequences, right, and then they developed some tools for analyzing sequences, and here if you go to search analysis, there is a tool called this pattern match. So, if you go with this pattern match, so you can give the pattern, right. I give the same pattern here, right, LIVM same, and if you submit, and you will get the sequences, right, which contain the particular pattern. So, if you click on this, any of these sequence, if you click, so you will get this the full sequence, and you can see the pattern this sequence. Where is this going to start from? Here, right, VKG, right, from here to here. So, if you check, this is L is here, and I is here, and two residues here, and then G, okay, this is a concept G, it is here, and E is here, and then K, right, and then A, and then E and T, right, and L is here, Y is here, and I, right, then 2x, right, V and K, and final G is final G. That is when this works, right, the program works. So, you can get this type of patterns and then see whether any specific pattern is important, right, for a particular set of proteins. I explained one example. So, this is your specific motif for the beta signal, that means for the insertion and assembly of beta barrel membrane proteins. This is a type of membrane proteins I discussed earlier, right. So, this type of motif is essential, right, experimentally they observed, computationally we can do this analysis using this search. So, here PO means polar. So, any polar residues, and here there is one X, so here put X here, so dot, and G, so G is conserved, and any hydrophobic residues is HY, and any X and hydrophobic here, and X and hydrophobic. Okay, there is a difference between this small HY and capital HY. Small HY includes the small residues alanine and cysteine, but capital HY it does not include this A and C. Now, the question is, why experimentally they showed that this specific motif, right, that is important, that is true or not. How to verify?
If it is present in all.
Right, it is present in that. First is, so first you take all proteins of beta barrel membrane proteins, and easily you can write a pattern, because if you go here and if you write this pattern, right, then you will get the list of proteins. Or other way you can do it, first download all the beta barrel membrane proteins, right, and then see whether this pattern is available or not. There are two options, one is the whole sequence you can search, or you can see whether this is important at the N terminal or the C terminal, right, mainly C terminal for the insertion. You can see, take the C terminal 40 residues and see whether the pattern is available or not. Fine. So, if you find this pattern, then you are happy. Then next question is how to verify this is important for this particular type of proteins. You have to compare. So, this should be present in this type of proteins, and but should not be present in other type of proteins. So, we can construct different data sets. Where shall we get the sequences? Unipro database, right. So, then we get the different sequences like normal globular proteins, you can see the inner membrane proteins, right, all beta proteins, right, different type of proteins you can construct and see whether the pattern is available or not. If available, then it is not specific. If it is not available, then it is very specific, right. When you do this, we can find this particular motif only for the beta barrel proteins, that means this signal is important for the insertion assembly, right, then we can find something. Likewise, you can define several motifs and you can see some novel patterns, and you can explain why this is important and what is the main use of these particular motifs in any sequences, right. You can do lot of analysis with different types of proteins.